Our next speaker is Karthik Duraisamy. He's a professor. Samir and Pooja call professor at University of Michigan. He's a director of Michigan Institute for Computational Discovery and Engineering, and he works at the frontier of scientific machine learning and scientific foundation models. Karthik, take it away.
Thank you very much for inviting me. So I'm going to be covering some recent work that we've been doing in advancing foundation models, agents, and moving these together towards the end of creating an ecosystem for AI-augmented scientific discovery. All right, so if you bear with me, I'm going to spend maybe a couple of minutes on the context behind what I'm going to be talking about. And you know, if you've seen over the past decade, there have been quite a bit of evolution in AI approaches as well as architectures, and I've shown some of them here. So at the same time, many scientific applications are proliferating. I think it's very fair to say that scientific applications have not had a ChatGPT-like moment, but I think it is also fair to say that at least in two cases, in my case, I'm pointing to AlphaFold and ForecastNet, we've had AlexNet type moments, right? Specialized AI architectures that have truly transformed the domains, right? But in many, many applications in science, we are found lacking in getting these things to work and to generalize. And I think one of the main reasons is compared to more commercial or more general applications of AI, data is very expensive and sparse. In many scientific problems, you have chaotic multi-scale and emergent phenomena that AI models have not mastered yet. And there is also the self-play loop, right? So in many problems, especially those where reinforcement learning has been successful, probing the environment, getting a quick result, and then changing actions is much more straightforward. But in many scientific applications, that's not the case, right? So what are we missing? Well, we need to maybe operate at the level of steerable concepts and principles, right, instead of some obscure latent space manipulations that we have right now. And current reasoning capabilities are impressive, but they're very brittle, as we all know. So there's a lot of work to be done there. And of course, there may be new architectures and abstractions that we need to develop for the underlying architectures as well, right? Oh, and certainly, especially in scientific applications, we have to be much more honest about terminology and evaluations. Almost every benchmark out there, or most demonstrations, do not address transformative applications. Okay, so anyway, I think the takeaway of that first thing is I pointed to some obvious limitations. But clearly, scientific progress and discovery does not require flawless AI. Even with current-day AI systems, we can do a lot towards automating science. And I'm going to talk about a couple of applications that we've been pursuing in the last year and a half. I keep saying that the most important component that we need to develop towards the kind of goals that I'm going to talk about is basically some kind of world model or oracles that maintain trusted knowledge, and they interact with trusted primitives, right? Trusted primitives could be physics simulators that we trust or surrogates of it, and AI systems need to interact with them in some kind of composable ways, right? And having some kind of self-consistency between these levels. Okay, towards that end, this is the kind of AI system we're envisioning. And this is the kind of thing we are building towards, and I'll show you a few examples. At the very top, we have current large language models like O3, O4, Claude 4.0. Those are the base reasoning engines. And ideally, we want them to be reinforced, tunable, right? Not just static models. Beyond this, we have domain-specific foundation models. I'm going to show you some examples, like specific foundation models for, say, chemistry or for materials or for biological processes, right? But the most important piece here is not the foundation models themselves, but if we are able to create some kind of a shared embedding space between these foundation models, then what happens at the intersection may be extremely powerful, especially if you're able to probe them, right? These foundation models and these reasoning models then pipe into this knowledge graph or a knowledge layer. Of course, this will also be fed by a very large RAG system, if you will. And then we have orchestration layer, right? So this is where much of the computational science community has been working very successfully over the past 50 years. We don't need AI to tell us, what the next best optimal experiment is when we've developed optimal experimental design techniques for the past 50 years, right? We have very powerful techniques for UQ, right? So this orchestration layer relies on well-founded, rigorous computational science methods that we've been developing, right? And these also have, human experts also have a role in this orchestration. And the final layer, of course, is where much of the work is done, the equivalent of test time compute, which is interaction of these models with high-fidelity simulations, experiments, some kind of formal verification, at least for parts of the workflow, right? And the key thing that I've shown in the left is the reinforcement fine-tuner, right? So all of these levels, ideally, should be tunable, right? None of these is very static. It's a dynamically adapting system that interacts with the real world, it interacts with simulators, it interacts with formal verification approaches, and adapts itself, right? So that's really the only way, in my opinion, we can move forward. I don't know how to go back. Well, how do I go back?
This is a small button.
Okay, yeah, so in my opinion, this is the only way we can move forward because we're never going to have the data that we need, right, to train a static model or even some kind of test time compute model. The only way these models can keep improving is by interacting with the real world. All right, so in the time that I have, I'll talk about 3 elements of that system that we've been developing over the past, as I said, year and a half. So the first one is a foundation model for molecules. So here, we're basically trying to generalize across material space and not just do embeddings, but also use those embeddings in very many different downstream tasks, right? And in this particular case, it's effectively a masked language model. And I've shown, on the top, I've shown you, on the top right, I've shown you the kind of, the scale at which we're operating. So working on about 50 billion molecules, and with a few billion parameters, that's the size of the foundation model that we have. And we're very grateful to all the resources that we've had access to. So far, the work that I'm going to show relied on about 1 million GPU hours. But the second time we do it, it's going to be maybe 10 times more efficient because we kind of know how to do this. And again, for lack of time, I'm just going to speed through this. This model does very well on many of the existing benchmarks. And in terms of interpretability, there are many, many different. I'm just showing you one example here. I think the first speaker spoke about interpretability and latent spaces. We have much more encouraging results to report, especially over the past 6 months, where anytime we are trying to look for phenomena, it seems that a kind of UMAP on the last couple of layers gives us a lot of information, right? In this case, how many benzene rings or clusters different types of molecules are connected to, right? Carbon atoms are connected to, so that's very easily revealed in this architecture. And as I said, that is interesting, but does not solve most problems. I think one of the most powerful things that these models bring to the table is giving multi-scale property predictions across atomistic structures, molecular structures, and even mixtures, right? So the mixtures part is extremely interesting because we are still training these models at the single molecule level, and then we are trying to now predict properties across, when these molecules are combined. So maybe I'll skip directly to that. So this is an example of how we are using these embeddings. As I said, we are training for individual molecules. So we kind of develop the embeddings for, say, if you have 2 molecules that are mixing, we get these embeddings for individual molecules, pass them through a neural network, and then we basically train a residual supervisory layer for the residual, and we're able to beat out pretty much any other method that exists. But of course, this doesn't mean we've tested across all possible mixtures, but for the kind of problems you're looking at, the embeddings seem to be extremely powerful. We've also used these for electrolyte molecule screening that is pushing us into spaces that we had not investigated before, which is encouraging. And we're not just stopping at unimodal foundation models, we're also doing foundation models for crystals at the same size. And currently, and hopefully in collaboration with Prasanna and others, we are now putting multimodal foundation models together. The second application I want to highlight is the idea of spatiotemporal physics, right? So many of these foundation models or any kind of AI system, for it to continually evolve, it has to build some kind of a world model, and in many cases, spatiotemporal physics is extremely important for AI agents. And the reason why I call this a foundation model is it's not just an AI surrogate. So these kind of models are being used for, say, as an AI surrogate. In the forward case, the same architecture is used for data augmentation. It is used for inverse problems. It's used for data assimilation. It's used for closures. And for this, we pursue diffusion models. And they have very amazing properties, and the most appealing of which is you can have one architecture, a conditional diffusion model, that does all of these tasks, of course, for a given class of PDEs, right? Not for all PDEs. And maybe one example I can highlight is in application numerical weather prediction. So here I'm just going to show you forward predictions. For instance, there are rare hurricane events, and we want to see how well we are predicting them. But as I said, in some of the publications that I mentioned, we have other applications as well under the same architecture, right? So one example here is, first thing I want to say is these models are as good as any existing numerical weather prediction solver, at least for about 10 days, right? Beyond 10 or 14 days, things fall apart, not just for this, but for numerical simulations as well. And this is not our discovery. This is a successful application that others have done in this field. And here's an example of how these models do. So this is application to a problem called Hurricane Lorenzo. And this is an extreme event. This is the easternmost Category 5 hurricane that was ever recorded. And we trained our model until the 2 previous years before the hurricane formed. And then we are able to not only get the formation, but also track the trajectory, right? So again, these models are getting very powerful, at least in doing very specialized tasks. Again, this is the architecture that I showed. Again, I showed you some examples of foundation models in 2 different domains. The exciting part is, what can we do with these things? And here is how we are instantiating this AI architecture in some kind of an agentic way. So the foundation models are in these yellow circles on top, a couple of examples. And then we are pairing them with a number of agents that are very specialized for specific type of tasks. And then we have a large language model like O3 controlling these agents. And we're also connecting all of these pieces to data generation mechanisms. Currently, data generation mechanisms are high-fidelity solvers, but eventually we'll bring some experiments as well. One of these examples we're showing here is, in this case, we type a natural language prompt in designing electrolyte for a vertical takeoff and landing aircraft. The foundation model that I showed earlier computes these chemical properties, and LLM summarizes it. The user asks some questions, further computation and optimization by these models and agents, right? So these are successful things that we can do with current day models. And of course, the most important piece then is, can we do computations that involve very many complicated workflows with these agents? And again, at least for specialized cases, in this case, density functional theory calculations for some very complex cases are being done by this agentic framework. And in many cases, we're able to do about as well as a human expert can do, right? So that doesn't mean we've solved the problem, but my main takeaway is, any current day AI system requires multiple layers. At some point in the future, some of these layers may converge, but my opinion is we are far away from it. But as long as we connect them in the right way, have access to, emulators of reality and steer them, I think we can have very powerful outcomes even in the present day, right? I'll stop with that, and we can take more questions later.
Thank you, Karthik.